Hi, I'm Tim Skell, Global HVACR Application Engineering Manager. Let's talk about harmonic mitigation techniques with a focus on system impact of an active front-end solution and how that compares to a standalone active filter-based solution. For today, we'll start out talking about harmonics as a whole, overviewing them just to freshen everybody up on the topic. Then we'll dive into harmonic mitigation techniques. We'll overview some of those most common solutions today, but then we'll focus on active front-end drives, or here at ABB we call those ultra-low harmonic drives, along with how that compares to a standalone active filter that's applied to a common bus. And then at the end, we'll talk about harmonic mitigation strategy. That'll be really more focused towards the consulting engineers to help give you some direction on what's the best way to specify things so later on in the project when you're going through submittals and verifying everything's good to go, to make that as painless as possible for you. So real quick, what is a VFD? It's something that takes fixed utility voltage, converts it into a variable voltage and frequency, and sends that variable voltage and frequency out to the motor. So VFD, variable frequency drive, because it's adjusting voltage and frequency. A high voltage, high frequency to the motor, it runs fast. Low voltage, low frequency to the motor, it runs slow. So the way a VFD works is essentially takes AC coming in, converts it to DC, chops up that DC waveform into a sinusoidal waveform down here, and sends it out to your motor. We will not really be talking today about this output side. So anything on the output side between the drive to the motor is not part of the harmonic, power line harmonic conversation. We'll be focusing on the input side of the drive, that process of how it takes AC from the grid and converts it to DC. That's ultimately what's creating the harmonics. As we look at the input side of our drive, we have our diodes here and our capacitors right here. So as I have three-phase AC coming in, and I'm just looking at one leg here to simplify it, it comes in, hits these diodes, and what happens is the diodes take that negative component and flip it up and basically make it positive. So that's your rectified DC voltage. If I had a linear load, so something like resistors, I would expect my DC current to basically follow my voltage waveform. However, that's not the case, because in this situation I've got capacitors. Capacitors act like batteries, they get charged up. And right here, as an example, is the charge of the voltage across the capacitors. So what ends up happening is the drive can only draw current from the grid when the grid power over here, which is that sinusoidal waveform, is higher than that red line, which is your DC bus voltage. So the only time the drive can draw current is in these little periods right here. So as a result, when you've got drives, they end up drawing current in gulps. So they're not sipping the current, the power from the grid continuously. They're gulping it. They're gulping that current. As a result, they're something that's considered a non-linear load. So any kind of application that's got power supplies in it that act like this are considered a non-linear load because they gulp current from the grid. What does current distortion look like? Well, typically I'd have the nice, beautiful sinusoidal waveform. In the case of having a lot of current distortion, I get something like this, where I've got these right here. Some people will call this bunny ear waveform. Some people will call it the classic double hump waveform. But the more current distortion you got, the worse these two humps are right here. So from a voltage distortion aspect, what does that look like? So this red line would be your nice, perfect AC voltage waveform. And then you notice this right here, this is considered flat topping. So that's a significant amount of voltage distortion on a waveform like this. And a lot of this has to do with the fact that the drive is only able to gulp current at the peak of this waveform, which helps naturally pull that down. Now just to go over a couple of definitions real quick that I'll be using. You've got total harmonic current distortion, or it might be abbreviated as THDI, or you'll see it THID. So that's really how much your current waveform is distorted. Then there's total harmonic voltage distortion, again THDV or THVD, you might see different abbreviations. That's how much your voltage waveform is distorted. And then there's total demand distortion, and that's really how much current distortion you have during the peak loading of your entire facility. IEEE 519 2022 is the latest and greatest standard, but there's actually been 4 flavors over the years.
1981 was the first version. It was all about voltage distortion, making sure you had quality voltage waveform that was more specific to the quality waveform that's ultimately going to be in your building. What they realized was it was hard to figure out if I had 4 customers next to each other and only one of them was really distorting the neighborhood. How do you figure out who that culprit was? His voltage is shared. So 1992 added a current distortion aspect to it, total demand distortion, to look at the current waveforms and what was acceptable there, because the current waveform is unique to each individual building. 2014 then did a little shift. It backed away from some of the voltage distortion levels. They still had the levels, but it put them so high that really, frankly, I wouldn't even want those levels in my building, even though IEEE 519 implies it's acceptable. And it focused much more on the current distortion, which is to figure out who the culprits are and making sure they're not going to put enough distortion back onto the network that they impact their neighbors. So 2014 and forward, it's really focusing on being a utility standard. Whether that's the right thing or not, that's a different conversation. But the standard itself is very much utility focused moving forward in 2014. 2022 made some updates, made it a little bit more modern, kind of prepping yourself for those alternate energy sources like solar and things of that nature. But for the conversation today, there's nothing really in 2022 that impacts it greatly for what we're talking about. One thing to give props to 2014 on is it did a better job on identifying the point of common coupling, the PCC. That's the point where the utility meets multiple customers. So you don't measure harmonics all different places throughout your building and then apply the IEEE 519 standard to those different points. It's really where the utility feeds you as a unique customer. That's the point of common coupling. And that's where these other standards really apply. So 2022, and it goes all the way back to 92. It's got your total demand distortion standard. So if you look at that table on the right, you got this ISC to IL. So it's your short circuit current to your load ratio. Basically, that's a fancy way of saying, are you a big customer or are you a small customer on the grid? Because if you're a big customer, your ISC to IL is going to be a smaller number. If you're a tiny customer, it's going to be a much larger ratio. Big customers have more stringent levels for what amount of harmonics they're allowed to put back onto the grid. Smaller customers, you can get away with a little bit more. And the reason is, as a small customer, you can't really impact the grid that much. But if you're a large customer, yes, that's when you can really impact the grid. Imagine my house, and if I'm creating a bunch of harmonics in my house, yeah, I'm really not going to impact the grid overall that much. But if I'm across the street from a very large factory, and that factory's putting a lot of harmonics back onto the grid, that factory is a much larger utility customer. They have much greater impact to the overall power quality.
So that was your really quick overview on refresher on drives, refresher on harmonics. Now I'm going to go into and focus much more on harmonic mitigation techniques. I like to start with this type of a slide that kind of shows results, because everybody wants to know about, well, how good is something compared to another solution. So this shows results of a couple of the initial types of mitigation we'll talk about. So I'm going to start from the left and work to the right. So if I have a typical drive and it's got no harmonic mitigation at all, I'm typically going to be in that 80 to 120% current distortion. So those are very significant numbers for a drive with no mitigation at all. You'll see I've got this other area right here. Sometimes what drive manufacturers might try to do is cheat a little bit, and they undersize their DC bus capacitor so that way they can't gulp as much at a time. And you can see lower current distortion numbers, but as a negative, it really impacts your voltage distortion. So it's not something I'd recommend. You see in both certain VFD designs and also with some of the more modern ECM designs are also trying to play that trick. The next step you do is you typically would put in AC line reactor in the drive or a DC bus choke from a harmonic mitigation, doesn't matter. Now you're typically going to be in that 35 to 45-ish% range, maybe 50%. And then you can also look at 18 pulse drives. I hope someday I don't have to give presentations involving 18 pulse. It's a very old way of doing it, but they're still around today, so I still talk about it. And then there's also passive filter designs, which are going to be in that 5 to 10% range, where you take a passive filter. And I'll talk all about these different solutions on the upcoming slides. I just wanted to kind of show you just from a graphical format, as far as when you have a drive with no harmonic mitigation at all, you're up in this range. And the reason there's such a wide range here is there's variability from one drive to another, depending on how strong my DC bus capacitors are as far as amount of microfarads, or perhaps I have a really stiff network, so I'm capable of gulping a lot of current very quickly compared to a softer network. So there's a lot of variables in here other than just the drive itself. That's why you see a bit of a range opposed to a specific value here. So this package right here, we're going to start with no harmonic mitigation at all. So you'll recognize from earlier, I've got these diodes and capacitors. There's no extra hardware in here or in here, so this drive's got no mitigation. So why do people pick these drives? Because they're small and they're low cost. There's really no other reason that small and cheap. Engineering considerations that I need to keep in mind if I'm allowing these drives in my project. They're going to have poor harmonic distortion, especially on the current side, and current distortion is what impacts your voltage distortion. They draw more current than their counterparts that have drives that have mitigation in them. They're also more susceptible to existing power quality issues because there's really no buffer in here. Later on we'll talk about DC bus chokes or AC line reactors that can provide a buffer in there. And also be very careful on those designs that have the smaller DC bus capacitors. Yes, they will show the lower current distortion. You may even see it all the way down to 30%, but it's because these guys right here are, in my mind, what I call undersized. They have just barely enough to do what they need to do. As a result of having these very small DC bus capacitors, it impacts the voltage distortion. You get these higher order harmonics, and these higher order current distortion harmonics really wreak havoc on your voltage distortion. So you can't just blindly look at current distortion ratings on products because depending what the harmonic spectrum is, it has different impacts on your voltage distortion. And from a customer, an end user, facility point of view, voltage distortion is one of the important things you're looking at. The next form of harmonic mitigation is adding impedance. That could be in the form of a DC bus choke like is shown up here, or it could be in the form of an AC line reactor that's put on the input side of the drive in front of the diodes. Either way, they both perform good initial drop in the harmonics. So if I look at how much does it help, it basically drops the harmonics in half. So it's roughly 80% to 40% ballpark. And this is an option that's standard in many HVAC VFDs. What do I need to keep in mind with these drives? From a harmonics point of view, it might not provide sufficient harmonic mitigation for all scenarios. So if I had 5 or 10% of my building loading with these type of drives, probably going to be okay. If I've got 35% of my building loading with this type of harmonic mitigation, no, I'm probably going to have to look at adding something above and beyond just AC line reactors or DC bus chokes. Also, adding that extra impedance is not compatible with the drives that have those small DC bus capacitors because you start having output voltage issues and you can also start seeing some oscillation issues. So if you have a drive that's got the small DC bus caps, you can't just put an AC line reactor on it and think you're good to go. There are still other issues. And now the 18 pulse drives. I mentioned briefly earlier that someday I hope I don't have to talk about 18 pulse drives. It was a good design 30 years ago, but it's a bit outdated. So the way an 18 pulse drive works is instead of having 6 diodes, which is a 6 pulse drive, it has 18 diodes. It's got this big old phase shifting transformer right here, which turns 3 phase into 9 phase. So now the drive is essentially rectifying 9 phase. So if I look at a package right here, this happens to be a picture of the demo that we have in our apps lab for when we talk about different harmonic mitigation solutions. This right here is a 20 horsepower package. It's the size of your refrigerator. And the part that's the actual drive is this guy right here. That's the drive. This is the phase shifting auto transformer right here. Here's your disconnect. And since we had to get this big box to fit this guy in it, we figured, well, we might as well throw a soft start bypass in there because we had a little extra room because you need a larger box because of this phase shifting transformer right here. So they're very large packages. What's good about them, if you got ideal lab type environment, you can get down to 5% current distortion under those perfect conditions. It's also a very mature solution. It's a robust solution. It's been around for many, many years. As far as other things to keep in mind, those perfect lab-like conditions very rarely exist in the real world. You're usually going to have a little bit of voltage imbalance, and this is where you end up having issues with 18 pulse drives. If you've got your legs of your power system might be say 481, 477, 472, now the results are not going to be nearly as good because as you look up here, This is all set up to kind of cancel harmonics out. This is why they're doing that phase shifting. And because the voltages are at different levels, they can't cancel out the way they would like. Now your current distortion levels end up being higher. So again, they need perfect conditions to meet that 5% current distortion. Also, of all the different solutions that I'm going to talk about today, this is the least efficient. And it's really because of the fact that instead of having 6 diodes, I got 18 diodes, and I've got this big phase shifting transformer, and I may also have balancing reactors in here too. So there's other things that involve that really impact the overall efficiency of it. And then the last part on it is doing retrofits can be a challenge. Depending on the manufacturer, there's different ways they do pre-charge circuits on the DC bus. So 10, 15 years from now, when the drive fails and they go to swap it out with the next generation drive, the pre-charge circuit may or may not be compatible with the new drive, or they might have had some custom boards in there. So I've seen some challenges with retrofits before where ideally an 18 pulse drive just made it more challenging. Now we'll talk about drive with a passive harmonic filter. So I've got my traditional drive here. The passive harmonic filter is an LCL filter, so an inductor, capacitor, inductor filter down here that helps, it's tuned to clean up specific harmonics. So positives about it, it can get you down to 5% current distortion with the top designs available on the market. That assumes there's a limited amount of voltage distortion in the background. You can also retrofit into an existing solution. So if the drive was already existing, you can get this in its own enclosure, stick it directly in front of the drive. Considerations to keep in mind, well, it's size, it's cost. You can see that in this picture here, you had to get a drive in a bigger box to include those components. Also, if you got a drive with a bypass, passive filters are meant to be in the drive circuitry only and not in the bypass, so that could involve a little bit more wiring out in the field if the filter is included loose. Also, I've seen far too many times passive harmonic filters, which are an input device, accidentally get wired up in the field on the output side because they think it's a DVDT filter. I wish I could say I've only seen that once or twice, but it's actually been far more prevalent than it should be. And then the last thing, and this is really important for systems that have backup generators, so hospitals, data centers, laboratory environments, airports, is you have to be careful with leading power factor because backup generators do not like leading power factor, and the capacitors in these circuitries in the LCL circuit really does generate a leading power factor at partial load. So what ABB does on our solution with passive harmonic filters is we have a contactor that we use to drop out the capacitor right there. So at part loads, this capacitor will drop out. It means the harmonic mitigation isn't as good at part loads, but it guarantees we're not going to have that leading power factor that could cause issues with the generator. Now I'm going to transition to talk more about the active front end or the ultra low harmonic drives versus active filter solutions, which is going to be the meat of the rest of the presentation. Now I'm going to add two additional solutions to this particular graph here. So I got active front end drives and active filters. So active front end drives are typically going to be in that 3 to 5% current distortion. Active filters, it depends on the filter performance and how it's sized. Typically you're going to be in the 5 to 10%, but sizing is a big impact on that. So if I start with the active front end drive or the ultra low harmonic, I've got my IGBTs here. And you thought, well, in those last pictures, weren't those something else? Yes. So in the last ones, those were diodes. Now with this type of drive, the active front end, it swaps the diodes out with IGBTs, and then combined with an internal LCL filter, this combination draws current linear from the grid. It does not draw it in gulps. It doesn't create harmonics and then have a filter clean it up. It draws it clean right from the get-go. So what kind of performance do I get? Usually around 3% current distortion or so. With the most modern designs, some of the older designs are around 5-6%, but the current design you get down to 3% if the drive manufacturers optimized it for harmonic mitigation. Some of the other advantages to this type of design and technology is you get unity true power factor, so a 1.0 power factor. Overall, the size isn't relatively much larger than some of the other solutions. At the end of today, I'll do a comparison of dimensions, and getting the active front end drive does not add a lot of size. It's generator friendly because it doesn't create harmonics in the first place. And yes, it does have an LCL filter, but the values are much different, so you're not getting that significantly leading power factor at part loads the way you would with a traditional LCL filter meant for harmonic mitigation. Other little side advantages to it, you can actually boost voltage. So if I had, say, a 460 volt line, I can boost it up to 470, 480 volt. That's something that you can't do with other drives, so that's kind of neat. I can also, if I wanted to, I can adjust the kVAR to be positive or negative. So if I had a system with a really bad power factor, I could force the drive to be leading power factor if I wanted to help out with the overall system power factor. So it's adjustable. It's pretty neat. Some of these designs can do regen or braking. And then what I personally like about it, just the simplicity. It's 3 wires in, 3 wires out. You're not adding any additional components. As far as engineering considerations, you can't retrofit it into an existing solution. So if you're going to use one of these drives, you have to choose it. You have to specify it right up front. If you installed a 6-pulse drive and you want to swap it out, you'd have to pull the old drive off and put the new drive on. So you want to specify these up front. Also, because you've got all this switching going on in the front end and the back end, your common mode voltages are a bit higher. So what ABB does is all of our active front end drives, ACH 580 or ULH drives used for the HVAC industry, all include common mode filters as standard. So that way you don't have to worry about that. And then the last item is that it's not as economical on fully redundant systems. So if I had a drive that was my primary and I had a second one of these is 100% as my backup, and my backup would only run 0.00001% of the time, it may not be as economical to have the backup also be a ULH drive, an active front end type drive. Now we'll talk about the active harmonic filter solution. So an active harmonic filter solution is not built into the drive itself. This is a facility applied, a bus applied solution. So it's more upstream from the actual harmonic creating loads. So if I look at my one-line diagram here, very simplified one-line diagram, I have this VFD here. There'd be lots of VFDs, other loads, different things that are creating harmonics. So if I look up here, I got that classic double hump waveform. What the active harmonic filter does is it's upstream. It's got current transformers. It's got CTs that are kind of monitoring what's going on, and it acts like noise-canceling headphones. It's pretty neat where it sees noise on the line and it basically cancels it out by injecting equal magnitude but opposite polarity. So basically it's fighting fire with fire. It's noise canceling headphones. So when do you use an active harmonic filter, a standalone solution like this? One is if you got a large volume of very small horsepower drives, it can become more economical because it's easier to clean up a whole, like hundreds of 3 horsepower drives with one large filter opposed to hundreds of small filters. Also, I like to use it if I have a situation where I have a building that's not within IEEE 519 compliance, and they're looking to bring the facility within compliance after the fact. Maybe they're getting in trouble with the utility. That's when an active filter is quite handy because you find a way to put that in, you tie it into your switch gear, and now it's making sure that that facility is not going to cause issues with its neighbors. It's happy from an IEEE 519 standpoint. May not have actually cleared up the core issues within the facility, so there's the negative of that, but the positive is you are now within IEEE 519 compliance. Engineering considerations to keep in mind here. It is the most expensive solution for most scenarios. So if you have your typical mix of small, medium, and large size VFDs and other harmonic sources in a building, it's usually going to be your most expensive solution. It is challenging to size correctly, and often you end up having it over or undersized because you're sizing it based on modules. So there may be a 50 amp module, a 100 amp module, a 300 amp module of harmonic mitigation that it can clean up. So if you start getting into these ranges, I need 310 amps, well that means I need a 300 amp module and a 50 amp module. So when you oversize it like that, that also adds to that expense of the solution. Also, you have to keep in mind coordination with gear and factory support specialists. When you take a passive harmonic filter and put it in the same enclosure as a drive, or if you have an active front end drive like the ULH, ultra low harmonic drives, the VFD manufacturer basically takes ownership of the entire thing. Where if you have active harmonic filters, now you're bringing in an additional specialist. So there's just one additional coordination person involved there. It is important to note the single point of failures. That's an important topic to be aware of for active harmonic filters. So one of the reasons you may use an active harmonic filter is because you have backup generators and you need your generators to have limited exposure to harmonics so that way your generator functions properly. if you have an active harmonic filter that acts as a single point of failure, and if the filter goes down when you go to generator mode, now there's a good chance your generator may end up tripping offline to protect itself due to instability. So when you look at single point of failure with active harmonic filters, you have a situation where the active filters do have protection features in there to protect themselves, and in some cases those faults it will auto reset. In other cases it requires a manual reset. So it might have been a nuisance trip that you have to go over and manually reset. Well, during that period where it's tripped offline, you really have no harmonic mitigation at all for your facility. You can get some redundancy. So let's say if I needed 300 amps, I could go ahead, instead of buying one 300 amp module, I could essentially have 300 amp modules. But you still have certain single points of failure where they're, say, for example, sharing a single CT, current transformer. So, but if you have an individual module go down and they're all sharing that same CT to get access, do your lockout tagout, put on your PPE, you're going to have to power down all those other modules, find a way to bypass that current transformer, so that way it can go to the still good modules and then bring the network up and get it working again. So there's just a little bit more coordination that goes on there. I mean, depending on the type of active harmonic filter, some of them have over 25 different fault scenarios. Lastly, I have listed on there unintended system interactions. This is one you may not know it's happening until it's too late. I can speak from personal experience. A previous drive manufacturer, we used to use active harmonic filters with the MCCs lineups that were full of drives. And whenever we did that, we had to essentially detune the harmonic filter, so have it not go after certain harmonic frequencies. And the reason was because it was interacting with the EMI RFI, the high frequency noise circuitry in the VFDs. So to get rid of that interaction, they had to detune the harmonic filter, so it was never able to get down to 5% THDI because of the fact it had been detuned. So again, that was before my time with ABB, but it's just one of those little unexpected nuggets that you can run into. So now let's take a look at decentralized versus centralized solution. So what I mean by that is, where's the harmonic mitigation occurring? Is it at the individual component that creates the harmonics? That's considered a decentralized solution. Or is it at a single point? That's a centralized solution. So if I'm looking at my typical commercial HVAC building, that is going to be, with an active filter, that's typically going to be a centralized solution because they're going to clean it all up at one spot. So let's take a look here on the right now. We've got protecting the grid from an outside the building perspective. Now, they both do a good job on that, so that's a wash. They both do a good job. How about protecting the building itself, preventing harmonics from propagating within the building? Well, that's going to be a decentralized solution. Now let's take a look at wire sizing, and we haven't talked a whole lot about that, so I'm going to look at an example here off to the left. So I've taken a look at 3 different ABB drives, so just taking data straight from a manual, so nothing that I'm making up here. So a 30 horsepower 480 volt drive, the 6-pulse version, it has an input current rating of 56 amps. When I add a reactor in front of it, so it becomes their ACH 580 drive, that's got DC bus choke, that's 44 amps. And then the active front end drive, the ACH 580-31 ULH drive, ultra low harmonic drive, that's got a 34 amp input current rating. So a 30 horsepower 480 volt drive, depending on the drive family, depending on the harmonic mitigation being used, I could have a 56 amp, 44 amp, or 34 amp current rating. Your upstream power wires, your breakers, things like that are all sized based on the input current rating. So you can see that this drive, because it's very low harmonics, can have everything upstream be smaller size. And then say this drive here that's got significantly more harmonic content to it. So in that case, your decentralized solution is the way to go because it's preventing the harmonics from occurring in the first place, and it allows it to have a nice low input current rating of the drive. So that also ties into not just the wire sizes, but fuses, breakers, gear, all things that can be upstream. How about losses over the wire? Well, that's also going to be the decentralized solution because my power losses, my I2R losses, that's all going to happen if I have high harmonic drives. So if I have low harmonic drives, I don't have those same losses across the wires. If I look at single point of failure, we touched a little bit on that in the previous slide. That's where the centralized solutions are going to give you a challenge, where you really have to be careful and make sure you have multiple modules in parallel, and then have a system in place where if an individual module fails, it doesn't impact the remaining modules, especially when you go to do service on it. So there's got to be a strategy in place for how you handle those CTs. How about if I wanted to bring an existing facility into compliance that was already failing? That's where your centralized solution, your active filter, is going to be the way to go, because you can add one individual component or multiple components in parallel upstream, and it'll take care of it from an IEEE 519 standpoint. It doesn't take care of the individual facility within it, but it gets you within IEEE 519 compliance. If I look at sizing of harmonic mitigation equipment, I'm going to say the decentralized solution wins that one every time, because by choosing a active front end drive, the manufacturer of the active front end drive figured out exactly what's needed within that drive to size it for a nice clean one-to-one harmonic mitigation. Really the only challenge in sizing when you do decentralized is making sure you do an accurate harmonic study. When I look at power factor improvement of my utility bill, they're both a wash there. Now the active front end drives have that 1.0 power factor. The centralized solution can also improve power factor. However, it does impact some of the sizing. So going back to that sizing conversation, how complex it is. When you get an active filter, you typically will choose it. Are you getting this because you want harmonic mitigation, or do you want power factor improvement? Well, if you want both, you have to size it for both. So you'll see some of the active harmonic filters out there, they actually let you put a priority in there. So you can say that I want the 80% of my effort, my capacity is going to be for cleaning up harmonics, and then 20% of my capacity is going to be for improving the power factor. So this just all adds to that sizing complexity. You got to figure out, well, am I looking to clean up harmonics? Am I looking to improve power factor? If I want to do both and do both very well, I need to make sure it's really sized appropriately, and that all adds up to that cost aspect of sizing active filters. And that kind of covers the next topic there, is you need to consider that power factor as part of the sizing of an active filter. It's not really part of the sizing of the decentralized solution. If I'm going with an active filter, I need to make sure I need to have an additional specialist brought on site to do the startup. Again, like I mentioned earlier, the drive guy handles the harmonic mitigation aspect if it's all part of the drive package. But when you go with the centralized solution, there's an additional player involved. Generator friendly, yep, they're both good with generators. Wiring independence for service, that one goes to the decentralized solution. I gave the example earlier about the CTs, where if I have a drive go down and it's got its own harmonic mitigation, yeah, that's that one drive goes down. Maybe I'm running it in bypass mode to keep that fan or pump running, but I'm really only impacting that one drive. If I have a centralized solution component go down, now I could potentially lose all of my harmonic mitigation that's going on for the entire facility, and now I could start having a lot of issues, and especially if I had that worst case scenario where my active filter was down and I needed to go to generator power, that's where you're going to have problems. How about free input power for submetering? So in today's world, we're all trying to figure out how we can save energy. Well, the very first thing you can do to figure out how to save energy is you need to know where your energy is being consumed at. So one of the neat things about an active front end drive is it's actually monitoring input power to the drive. It can tell you fairly accurately what amount of power that drive is consuming. So if you look at all your different air handlers, all your different pumps, all your different VFD driven equipment, you don't need to buy a bunch of separate submetering power meters. You just look at that information over, say, Modbus or BACnet, and that information will all be free available over the drive's communication protocol. And this last one I'll show you on the upcoming slides is increased cost when it comes to tiebreaker systems. So we already talked about active filters. The concept is really cool with the noise canceling headphones. They do a good job in most situations. Sizing is one of those challenges. And then in the situation where you have tiebreaker networks, you have to even oversize it even more. Now let's take a look at some one-line diagrams here. So what I'm going to do is kind of walk through this. So I have my utility power. This would be a transformer that steps it down from, say, 13.2 kV down to 480 volt. My automatic transfer switch, which determines which side of which power source my network is getting. And then I have my backup generator. So I'm going to kind of build off of these. So just a kind of a starting point is everything I'm going to look at is total harmonic distortion from the current aspect. I'm not going to talk about other loads in the facility, at least not at first, just to kind of be able to do an apples to apples comparison. So first off, I'm going to just assume a bunch of drives. I got 300 horsepower pump drives over on this side. We'll say I got 300 horsepower of fan VFDs over on the right side, and we're going to assume no harmonic mitigation at all. So that means each individual drive, if I measured it at the lugs, it'd be at 80% current distortion. And for my simplistic example, I'm just going to exclude all the other loads in the facility. And you can see that all the way up to here, I have 80% current distortion. I gave the example earlier about the 30 horsepower drives and the different input current ratings. If you look at your harmonics, if you have 80% current distortion, that typically means it's about a 1.28 times oversize factor for your fuses, your breakers, your wires. So that's what this red is indicating. I need to oversize all of this because of the high harmonic content. So I'm going to add another example, very similar. I'm not going to touch these drives here on the left, but I will add reactors to the drives on the right. So I still have my 80% current distortion coming up to here. I've got my 40% current distortion here because I added reactors. I got the drives with the DC bus chokes built into them. And now I've got 40% current distortion, 80%, so overall it averages out to be 60% because I like easy math. That's why I made everything 300 horsepower here and 300 horsepower here, so I can do the easy math and average those together. You can see I still have to oversize, but that oversize is smaller. It's a 1.08 times oversizing factor. Now let's take a look here, and I'll leave these with the reactors because I just put drives with reactors over here. And I'm going to take these drives that had no mitigation at all. I'm going to replace those in this study, assuming drives that were active front end solution. So now instead of being 80% current distortion on each drive, it's only 3% current distortion. So now I kind of look at here and I work my way up, and now my system is coming down at 21.5% current distortion. So it's not nearly as bad as it was earlier. And if I go back to that oversizing conversation, you can see that with the 3% current distortion, there's really no need to oversize at all when you actually go ahead and do the math. And then if I went ahead and changed all of them out to active front end drives, now I've got 3% current distortion on this bus, 3% on this bus, works all the way up. I have nothing highlighted in red because there's no need to oversize anything. There's no harmonics being created because the active front end drives prevent harmonics from being created in the first place. If I was looking at a cost optimized solution, I might look at something more like this. I don't necessarily need to put active front end drives on everything. I might do it on some drives over here. And these over here, I might have a mix of drives with reactors and drives with active front ends. So maybe some of my 15 horsepowers would have reactors and my 20 horsepowers would be the ultra low harmonic active front end drives. So then at the end of the day, it all averages out to 5%. Again, in these examples, I'm not showing other loads in there. I'm just trying to keep everything nice and simplistic to visualize it. Now we'll go over a centralized solution where it's an active filter. So in this case, I got a single active filter, and my whole network is full of drives that have 5% equivalent impedance in them. So AC line reactors or DC bus chokes. Pro tip on that is the active filter manufacturers are going to recommend the drives always have impedance in them. They don't want to deal with the drives that are the 6 pulse with no reactors because those have the 80% current distortion, and it's going to be significantly more harmonics that the active filter has to clean up. So they're going to want the drives to come with reactors in them so they don't have to essentially double the size of the active filter. So it helps with some of the sizing by having the drives with reactors in them. Even with that 40% current distortion, you still have a little bit of an oversize factor on your wires and your cabling and everything upstream, but it's not as bad as those drives that are 80% current distortion. So as I've got my current distortion coming upstream, my active filter, essentially noise canceling headphones, takes care of it. So then upstream of it is only 5%. My utility is happy. So now let's do an example where let's say lightning strikes and it knocks out utility power, also created a transient on the line that caused my active filter to trip out. So active filters, they've got faults in there to protect themselves. Some of them auto reset, some do not. So if it's not a auto resettable one, somebody's gonna have to come up and physically reset it on the unit. So lightning strikes, my active filter trips offline. My automatic transfer switch, once the generator spins up to full speed because there was no utility power, my automatic transfer switch switches over to the genset. Genset is now seeing 40% current distortion because of the fact that the active filter is offline. now that generator is probably going to trip offline because the voltage regulator is not going to be happy, and it's going to have to trip offline to protect the generator. So here you've got a critical application. This whole reason you invested in a generator, and it's not able to run because of all the harmonic loading in the facility. So just something to keep in mind when you're designing these systems. Whenever you have that single point of failure, you need to make sure that you're able to reset those faults quickly. Make sure maybe you've got multiple of these active filters in parallel. Otherwise, you're going to these situations where your system's just going to be down. So now I'm going to take a look at a system with additional electrical devices. So I'm going to keep it simplistic, just added a box off of the one line for everything else. So in a normal situation, active filter's functioning. I got utility feed for my power. Active filter's doing a good job dropping the current distortion down to 5%. Everything with size good to go. We're going to make that assumption. Voltage distortion of the transformers is brought down, so that's good because your current distortion creates voltage distortion. So everything is good at the utility level. You will have, though, a little bit of voltage distortion being generated and fed over to these electrical devices, because what happens is with current distortion creating voltage distortion, you still have all this current distortion working its way up through the network. So depending on the lengths and the impedances and size of these wires, that all is one of those variables that impact how much that voltage distortion is. There's really no way for me to answer that because there's just too many variables in the system. And then we have the situation where if the active filter does go offline, it's being serviced, tripped offline, whatever the situation is, now your current distortion is now all the way up to 40% of the utility, but that's also creating lots of voltage distortion at this transformer, and now that voltage distortion is definitely going to work its way down, and you have that bad voltage distortion going into your other electrical devices. So how do I take care of that? Well, what I could do is add additional active filters. So now it's less centralized, and I'm slowly going towards a decentralized solution. And now I could add an active filter right here. So when I add an active filter right here, now I'm essentially protecting the upstream from this active filter. So even if this guy was to go down, this one is still helping to some extent. It may not help with all of the voltage distortion, but it's going to add an additional buffer in here. So you can add additional active filters throughout the facility. You just start adding more and more cost to it. So now I'm going to take a look at basically the exact same scenario, but instead of having drives with reactors and active filters, drives where it's a decentralized solution, and I'll use active front end drives as my decentralized solution. So we'll make the active filter version go away, and we'll focus over here. So now I don't really have any more of a single point of failure because I'm not creating harmonics in the first place. It's only 3% THDI. I'm never going to have to worry about single points of failure or adding multiple layers of harmonic mitigation all over because my drives aren't creating harmonics in the first place. And that's one of the biggest advantages of that decentralized solution. My last example I'm going to give today is going to be on systems with tiebreakers. So I'm going to look at two systems, one with active filters, one with active front-end drives, and a decentralized solution. So starting with the centralized active filter solution, I basically have a larger facility. So I got a utility feed over here, I got a transformer feed over here, and a bunch of drives. I have another transformer and a bunch of drives and the rest of my electrical system over here. So it's kind of split up 50-50. And I've got this guy right here, it's called a tiebreaker. So when everything is good and happy, this guy is open. So this transformer feeds this side, this transformer feeds that side. Now let's say something happened with this transformer. It was no longer available, it became damaged, fuses popped, whatever the situation is. Now this guy is no longer able to feed this side. What happens is this tiebreaker closes, and this transformer for a very short period of time is now not just feeding this part, it's also feeding this area over here. Typically these transformers are oversized a little bit, and they're looking at it saying, you know what, I'm not going to be running like this 24 hours a day, 7 days a week, 365 days a year. It's just I'm going to really push this transformer for a short period of time until I can get things up and running over here. Because you're really pushing that transformer in that situation with this tiebreaker close, which now feeds everything, you need to make sure that transformer can survive and last that. So the last thing you want to have is this transformer now being fed or being exposed to additional harmonics. So traditionally, This active filter was sized to take care of the harmonics for this portion, but if I got a tiebreaker, not only am I sizing my active harmonic filter for these drives, I should size it for the worst case scenario of all of these drives too, because this guy's not helping me anymore. He's taking things upstream. Well, that upstream is not working anymore. So now I have to make sure that this active harmonic filter is sized to handle this load and this load. So we're already looking at active harmonic filters being the most costly solution. Well, now I just took the most costly solution and had to oversize it on top of that to handle this situation. So again, tiebreaker systems, you have to consider how that utility transformer is going to deal with that overload scenario and how you're going to size that active filter to help out that transformer during those scenarios. Now we'll look at the example, same thing, but instead I have active front end drives down here. So I've got the low harmonics in the first place. I'm not creating the harmonics. I have my normal system. It's this half over here, this half over here. Now let's say I lose my utility power over here, lightning strike, whatever it is, and tiebreaker is closed. Now this transformer here is now feeding everything until they can get this guy up and running. But you notice because I have low harmonics right from the get-go with my decentralized solution, everything's nice and low at 3% current distortion because that's how what the drives are generating in the first place. There's no need to have to worry about having third-party devices oversized to handle this situation. So in other words, it doesn't matter if the tiebreaker is open or closed, the drives and the harmonic mitigation are all ideal for that particular situation of a tiebreaker. Okay, now we'll have a little bit of fun. So I always like the psychology test. So my question to you is for you to figure out, are you an active front end, or ULH, or are you an active filter kind of a person? What kind of person are you? So here's the scenario. Your teenager's in their room and they got their music cranked up loud. Everybody in your house is annoyed. Your windows are open, and in the past, your neighbors have commented about unpleasant music. So again, kids in their room, music's cranked, nobody in the house likes it, windows are open, and you've had complaints from your neighbors before. You've got two options. You can put on a pair of noise-canceling headphones and shut your windows, or you can ask your teenager to turn down their music to an acceptable level. So those are your two options. Which one would you pick? If you said number one, you're an active filter kind of person. You aren't bothered by the noise anymore because you got your headphones on, your noise canceling headphones on, and you shut your windows so your neighbors don't hear it anymore, but everybody else in the house is still stuck listening to it. If you said number two, then you're an active front end kind of person. You're a decentralized solution because you stop the excess noise from being generated in the first place. And while at it, your solution is a bit greener because all the electricity isn't being wasted maxing out the receivers and the speakers in your kid's bedroom. So that's my fun psychology test. Are you an active front end or an active filter kind of a person? To kind of wrap up today, I want to spend a little bit of time with harmonic mitigation strategy. So how to specify harmonic mitigation? Well, first we have to kind of look at what are we specifying. So IEEE 519 is one of the most common ways to specify harmonics, but really who's responsible to make sure the facility is within compliance? You really don't want to look at the lowest bidder from the contractor point of view because you don't want the lowest bidder determining your mitigation. You don't want to look at the lowest bidder from the equipment manufacturer either. So ultimately you want to look at the consulting engineer wants to kind of take ownership of really what's required. So some of my recommendations I have for the consulting engineers out there or those who are working with the consultants is do the harmonic analysis up front. So that way we know what mitigation is required. And then you can determine which way to go. Do you go with low harmonic drives on everything, low harmonic drives on larger loads, standard drives on the smaller load? Maybe you can get away with standard drives on everything. Or maybe it's standard drives plus an active filter. So each system is a little bit different. We have tools that kind of can take a look at each system and figure out what's optimal. When you start cleaning up harmonics and doing studies, my recommendation is you always look at the biggest loads first. So if I got a 3, a 30, and a 300, I'm going to start at that 300 horsepower, then my 30 horsepower, and then only look at the 3 horsepower last if I still need additional mitigation yet. I also noticed I like to talk about loads instead of just drives too. So you'll see situations, especially with fan arrays, where I might have four 10 horsepower fans, so I got 40 horsepower total, where somebody would have said, well, for a 40 horsepower drive, I would have put additional mitigation in there, but these are only 10 horsepower drives, so I don't need it. Well, if I got four 10 horsepower drives, that's the same system impact as a single 40 horsepower drive. So definitely keep that in mind when you're looking at applications with multiple motors. Treat it as a total load, not as an individual drive or motor size. Also, recommendations I have is source all your drives from a single point of responsibility, because otherwise, if you get some of your drives locally and the rest are OEMs, you got one OEM who's looking at the air handlers, another OEM's looking at the pump skid, another OEM's looking at maybe just a cooling tower drive. There's no one person looking at the entire system. So if you get all your drives from a single point, at least you can work with that single point of responsibility on your harmonic mitigation conversation, because the OEMs are really just going to look at their scope and not the overall system. I always like when you do that harmonic analysis up front, you create a VFD schedule that identifies what mitigation is required on the job. The reason is, as contractors, they love to look at specifications as recommendations, and they look at the schedule as the actual answer key. So if you have a drive in the schedule and the drive says active front end, you're much more likely to get what you're asked for by having that in the schedule than trying to just enforce that via a specification. Also, as much as I love IEEE 519, remember that's caring about protecting the utility, the grid, the neighbors. You as the consulting engineer, if that's your role, you are responsible for your customer also. So you need to still consider voltage distortion. Don't just get hung up on the current distortion. Here's an example of a VFD schedule. I'm not going to go through this in detail, but the beautiful part about it is you can put tags of the VFDs, what it's servicing, quantity of motors, the enclosure rating of the drive, what harmonic mitigation is needed, whether it needs a bypass or not. A lot of great information here that helps the folks out who are bidding a project. Now I'm going to do one of my favorite topics, the harmonic bar hopping analogy. So my goal here is to help show who should be responsible for keeping harmonics low. What individual is that? So we're going to first have me going out doing a pub crawl. So I stopped at the first bar, had a couple beers, stopped at a second bar, had another beer, but a different type of beer. Stopped at my third, had a couple rum and coke. Stopped at my fourth bar, I had a shot. Yeah, it's a good night so far. Night's starting to wrap up. I have my little tester. I blow in it. I blow a .11. Realize, yeah, I'm not driving home. I better go get myself an Uber or whatnot and get home that way because I can't drive anymore. So I'm blew a .11. Who's at fault for that? Was it the bar? Well, I went to different bars. Was it the alcohol brand? No, I went to different. I drank different types of drinks. But even if I went to the same bar and I drank the same drink all night long, is it really that bar's fault or is it really that drink's fault? Not really. Who's responsible for me? Well, I'm responsible for me, right? Same thing for you. I'm sure you guys would feel the same way. So what are the strategies for me to stay below a .08? Well, I could figure out how much I should be drinking that night, pace myself, figure it out ahead of time, i.e. make a VFD schedule. Or I could have drank non-alcohol beer all night long or use all ultra-low harmonic drives. So those are different types of solutions. So I gave a little teaser there into the next part of the analogy, but if I look at my BAC, that's my harmonic content. My beverages, that's my VFDs, the source of harmonics. The bar is how I'm getting my VFDs. My body is, say, the commercial building that we're talking about. And my brain, who's responsible for me, my brain, that's the consulting engineer. So if I flip this example, my air handler OEM provided a couple of VFDs. My pump skid guy provided a couple of VFDs. Maybe they're even a different brand of VFD. The local VFD rep provided some VFDs. And then the chiller OEM provided VFDs. Well, it's really hard for you to point your finger and say, well, if the system's not in compliance, whose fault is it? Because if you look at any of those individuals, they're all going to say that their scope of what they provided was good to go. So I like to use this example to show that you don't want to get your VFDs all sourced by various people unless you have a very, very clear VFD schedule and you enforce it on what needs to be provided. I'm going to wrap up a little bit just dimensions because whenever people talk about adding harmonic mitigation, physical size is always one of the things that come to mind. So let's look at the active front end drives, those ULH drives. How much physically larger are they compared to other solutions? So my first image here on the left is of a 6 pulse drive with impedance, so kind of your go-to drive. and it's got a disconnect on the bottom here. So a typical solution, drive with disconnect, just under 30 inches high, 6.4 inches wide. In equipment rooms, the width is really your key dimension you're watching. Height and depth usually isn't quite so critical, so width is your key one. So your standard solution is 6.4 inches. If I went with an active front end drive, so if this is a 15 horsepower example, I only went to an 8-inch wide enclosure, so I'm less than 2 inches wider. Very little depth impact. But if I'd gone with a 6-pulse drive and put it in a box with a passive harmonic filter, now I'm going up to 16 inches wide, so I'm over double the width of my original solution, where if I went with an active front end solution, I didn't really add much width. Now I'm going to go up to a 60 horsepower. Started out my standard drive was 8.4 inches wide. My 60 horsepower active front end is only 10 inches, so 1.6 inches wider there. But my drive with a passive harmonic filter is 19.3 inches. So again, it's over doubled the width because of the passive harmonic filter. Again, the ultra low harmonic drive is a smaller solution than the passive harmonic filter. Lastly, I will show a 150 horsepower example. In this case, my 6-pulse drive is 28 inches wide. It's a little bit a little wider box. And the active front end drive ends up being smaller because it went with a tall, skinny box for our standard solution here. So again, ultra low harmonic drives do not add a bunch of physical size and space requirements when you're looking at a just standard solution like a drive with a disconnect. So today we started out talking about how a VFD works, how it draws current in a nonlinear fashion. It gulps that current. When you gulp that current, it creates current distortion. Current distortion is what leads to voltage distortion. IEEE 519 cares the most about current distortion, but from a facility perspective, a consulting engineer responsible for making sure you're not going to have problems in a building, or if you're a chief engineer for your building, you're really caring about voltage distortion because that causes the biggest impact on your end. Talked about different ways to clean up harmonics. You got your standard 6-pulse drives. You can have impedance built into them. You can add passive filters in front of them. You can upgrade to an 18-pulse drive, or you can add bus applied active filters to the entire facility, having those single point centralized solutions. Otherwise, my preference, I mean, yes, ABB offers all of those different solutions, but my background being an electrical guy, I'm naturally going to gravitate towards those active front end solutions. Also, it's called ultra low harmonic drive in ABB lingo, and it's really because I like to clean up harmonics before they even start, so that way I don't have to worry about it upstream. So if I look at that active front end versus active filter, active filters are good for fixing an existing IEEE 519 problem to get an existing failing building up into compliance. But if I'm doing any kind of new projects or I'm trying to protect the facility, that's where I'm looking at using active front end drives or ULH drives. And lastly, we talked about harmonic mitigation strategy. From a consulting engineer's point of view, my recommendation is make sure you have a clear specification and schedule. Ideally, do the harmonic analysis up front. That way you can fill out the schedule and identify what's needed, because it's going to make submittal time a heck of a lot easier and you don't have to rely on the lowest bidder to determine what harmonic mitigation is needed.